So our next speaker is a very old friend. Okay, not so old. I'm the older brother. We had the same supervisor, so it's a great pleasure to have you here. So Diana, she's an astronomer, and she's PhD in science by the Institute of Chemistry of the UFRJ. Okay, she was professor at Univap, and now she's a joint professor at Observatório do Valongo. Okay, she's expert on astrochemistry, especially on the study of the chemistry on ice and also interstellar dust. And she's also working on the study of the formation of prebiotic molecules in astronomical environments. So it's a great pleasure to have you here, and let's enjoy her talk.
Okay. Good morning. Thank you, Marcelo, for the invitation. It's okay, the sound? I will speak about the DNA in Titan, and this presentation is divided in two parts. The first, I will speak about the clouds, the sea, and the Titan tollings. And after, I will speak about our work, about the DNA in Titan. So, Titan is a moon. It's larger than the Mercury and Pluto, is a big moon. Titan has a dense atmosphere, is larger than the Earth atmosphere. Because the dense atmosphere, the solar ultraviolets are mostly absorbed, only a little quantity will reach the surface of the Titan. The predominant species in atmosphere of Titan is molecular nitrogen, N2, and methane, CH4. But due to the energetic particles coming from Saturn magnetosphere and solar photon, there are a lot of ions and radicals due to the association. Titan has dunes, lakes, channels, mountains, is an activity place, resembles our planet. But the liquid in Titan is mainly methane, instead of the water in Earth. And the surface is frozen, is condensed, a surface is iced. In Earth, the surface is silicate, and the reactions can occur between silicates and molecules. In Titan, the reaction will occur between ice and water ice, and other molecules. It's a little different. In Titan, there are large liquid reservoirs. The atmosphere is nitrogen dominated, 95% of molecular nitrogen. In Earth also, but in Earth is 28% of molecular, 78% in Earth of molecular nitrogen in Earth. But in Titan is a little different. of the Earth because Titan has little oxygen. In Titan, we have 5% of the atmosphere is methane, and there are traces of other gases, includes methane, but there are other gases. And the temperature in surface is around 95 Kelvin. Well, in Titan, we have clouds, and depend on the altitude, the clouds will be formed by different mechanisms. In stratosphere, the composition of the clouds is different of the troposphere, for example. In the clouds, the ice particles are made up of a variety of compounds containing hydrogen, carbon, and nitrogen. In the stratosphere, the dominant compound in the clouds is the dicyanoacetylene, C4N2. This compound is responsible for the brownish-orange color in the atmosphere. So the appearance of this kind of cloud goes against everything we know about the way clouds form on Titan, because and in our planet also, because when we think about the clouds in our planet, we think in the cycle of evaporation and condensation of the water. The same occurs in Titan, but the cycles of evaporation and condensation is with methane in the troposphere. But different condensation process can occur in stratosphere. For example, if we think about the formation of dicyanoacetylene in Titan stratosphere, we need to think about the solid state chemistry, because it's the way to explain this formation, molecular formation in the clouds. So to explain, I show you a scheme here. So the ice in the clouds, the particle ice in the clouds, have an inner layer of cyanoacetylene, HC3N, and is covered with a layer of hydrogen cyanide. Here is the cyanoacetylene, and here the hydrogen cyanide. Okay. So when the photons interact with the ice, produce radicals, and the radicals C3N react with the HCN and produce the dicyanoacetylene. There are others pathway of the reaction, but this is the main. So this show that it's important to understand the solid state chemistry in Titan. Almost 50% of the total Titan surface are in liquid form. Titan has seas and lakes. Here I show you the second largest body liquid in Titan. The composition is mainly methane, is methane rich, but has seabeds covered by a sludge of organic rich material, also in the lakes and sea. In the atmosphere, nitrogen and methane react and produce new molecules. These molecules, the heaviest of these molecules, fall to the surface, will reach the sea. A part will be dissolved in the liquid methane, a part cannot be dissolved and tend to sink to the sea floor. Well, during the last 4.5 years, these photolyzed molecules that was in atmosphere, that were in atmosphere, have been deposited on the Titan surface. And this process will produce layers of organic toluene. The toluene can react with the ice in the surface of Titan and produce organic species with oxygen. The general formula of toluenes is like this. There are carbon, hydrogen, and nitrogen. This toluene is produced in the atmosphere and aerosol particles in the atmosphere. And when reacts with the water, produce oxygenated molecules. A lot of work investigate Titan toluenes produced for energetic discharges, UV photolysis and radiolysis in the literature. I put a list here, but you can find more works. But the photochemistry promoted by soft X-ray in primitive atmosphere was poorly analyzed, because this we investigated with this word. So in this word, we studied the effect produced by soft X-ray and secondary electrons in Titan aerosols, analogs. We made a solid mixture compound mainly of molecular nitrogen, 95%, and methane, 5%. And we put traces of water and CO2. The results are in this work. And beside me are also in the work Sérgio Pilling from Univap, Álvaro Neto, Roberto Hittner, e Arnaldo Naves de Brito from the Unicamp, Campinas University. So, first, we radiate the aerosol analogs in situ in a chamber, vacuum chamber. Here is a scheme. The experiments were performed in Brazilian synchrotron light lab, located in Campinas, in Brazil. We used a high vacuum chamber coupled to soft X-ray spectroscopy beamline. We use the SXS beamline. And we employed a continuum beam from visible to soft X-ray in this range, 0.5 until 3 keV. So here we have a chamber, the first chamber, where we made the mixture nitrogen and methane. We can analyze the atmosphere all the time with this analyzer. And the mixture goes to another chamber, and in this chamber there is a substrate. The substrate was 15 Kelvin, and the gas will condensate and condense in the substrate. Okay. So the photon beam will interact with the sample. The photon beam is here, okay, and will interact here. And after we can, after irradiation dose, after each irradiation dose, we have a new infrared spectrum. The analysis in situ was done with infrared spectrometer. So, during the deposition and irradiation phase, the pressure in the chamber was around 2 times 10 a minus 6 millibar. So, in this case, we have one monolayer of the mixture, nitrogen and methane, per second adsorbing in the substrate, okay? All the time for 73 hours. But if the chamber was totally closed, the pressure basis was about 8 times 10 a minus 8 millibar. So we can form a monolayer of water and CO2 after every minute. So in our experiment, we have one monolayer per second of the methane and nitrogen, and per second, and one of water and CO per minute. These residual water molecules supply an oxygen source in Titan, for example, simulating possible cometary delivery. Here I show you the beamline photon flux as a function of photon energy in SXS in comparison with the solar photon flux at Titan orbit. So the integrated flux in the sample, in our sample, It's around 16 photons per centimeter square per second. And in Titan is around 10⁷ photons per centimeter square per second. So around 9 order of magnitudes lower than the SXS beeline. So in this experiment, we simulate 7 million years of exposition in Titan, X-ray exposition in Titan. Here, the absorption coefficient of some constituents of the Titan. So to form C+, we need 25 EV. To form CH+, we need, from this the methane, we need around 20 EV. So to CH2+, 50 EV. So if the energy, the photon energy is low, around 10 electron volts, the reactions will be driven by the neutron-neutron reactions in this region. If you have energy between 10 until 14 eV, the reactions will be driven by neutron radicals and radical pathways. And for higher energy, higher than 50 eV, the species will be ion neutron and ion radical species in the reactions. So in the soft X-ray case, the energy between 0.1 until 10 keVs. Secondary electrons will be important too in the reactions because will be produced a lot of secondary electrons after the interaction. During the experiment, we saw A2 enhancement in the residual gas. This suggests photodissociation of methane in gas phase. So some gas phase photochemic was also occurring inside the chamber and not only in the ice. So after the irradiation phase, the sample was heated until 300 Kelvin, and another spectra were collected because we was interested in the chemical chains promoted by the thermal heating. Similar heating can occur in Titan during a comet impact or volcanism events, for example. The chamber was, we put dry nitrogen in the chamber up to the atmospheric pressure to open the chamber. And we removed the substrate and we sent the organic residue, the toluene, to the chromatography and to nuclear and magnetic resonance analysis. So this experiment had part in situ. In situ, you used the infrared technique, and a part ex situ when you used chromatography and nuclear magnetic resonance technique. So about the results using infrared spectrometry in situ, you can see here infrared spectrum of the sample during the irradiations. Here is the number of hours of irradiation. In red, 1 hour. In blue, 5 hours. Black, 40 hours. And the last, 73 hours of irradiation. So you can see a lot of features. For example, around 2,100 centimeters -1, we can see the CO street modem. Broad feature at 800 centimeter -1 due to the water. Methane deformation here. Several features associated with nitriles here around in this region, okay, and C8N and aromatic C8N here. In the beginning, there are not C8N or nitrates, but during the irradiation, these species will appear here. Here you can see also another set of spectrum. We are comparing difference between infrared spectrum in different temperature. All the spectrum. We use the same sample, but we heat the sample. Here, the ice after 73 hours of irradiation in red. So after the heating, 200 Kelvin and 300 Kelvin black. So the nitriles around here in this region are present until 200 Kelvin. After the nitriles are not here. But there are organic trace bands at 300 Kelvin due to associated with hydrocarbons here. Okay. Maybe we have esters here in this with this band. The CO mode of ester is found in this region, and there are several unidentified features. Maybe CN aromatics can't bring this. I don't know. Here are indicated the location of some vibration modes of the adenine. Only to compare, but we didn't find strong evidence of adenine in this sample using the infrared spectrometry. I show you here a variation of the column density of the some molecules observed during the radiation. Here we have nitrogen, molecular nitrogen, CH4, water, CO, CO2, and the ion OCN. So here about the CO and the CO2, the abundance of CO2 is 10 times lower than the water in the experiment, in the beginning of the experiment. The CO is very low, the abundance of CO is very low. The CO observed in infrared spectrum is mainly due to the CO2 processes. In the beginning, the CO abundance is almost zero, but it's low, very low. But after the first hour of the irradiation, a fraction of frozen CO2 is converted to CO, and you can see here. We can see CO in the experiment after some time. After 15 hours, the ratio CO-CO2 reached constant. It's constant, around 3.5. And in this moment, the number of CO produced by CO2 is equal to the amount of the CO2 produced by CO. The CO column density is still increased because we have a continuous deposition of CO2 from the chamber, okay, in the substrate. The OCN ion is also present in our sample after the radiation. This ion was observed by Moore and Woodson in an experiment involving proton irradiation and UV photolysis. And this ion is observed until 200 Kelvin, but evaporate after this. And after we sent the material to chromatography, and here I show you a spectra from the chromatography. Is a chromatogram. We compare our sample, Titan tolerance analogs, with several molecules, several amino acids, and DNA bases, but we did not find amino acid in our sample. Here is the spectrum of Titan tolerance in chromatography. When you compare with the adenine spectrum, we found the feature. So this signal here, okay, in chromatography. So, and here I show you the chromatography, the time in the chromatography, and the mass spectrum also. So if we compare our sample and adenine, if we compare the mass spectrum and the time, we found the same features like the adenine. Okay. So another part of the tolling we sent to nuclear magnetic resonance. Here we have a spectra of the Titan tollings and adenine using the nuclear magnetic resonance, and the features of adenine are here in our spectra also. So we found the same value of the chemical shifts for the aromatic hydrogens in the case of Titan and adenine. Titan tolling analogs and adenine. So we have the results, and we need to think about what is happening. So we compare our results with others' works. So there are a lot of works using thermal heating and electric discharge, and in that work, adenine is formed. So adenine and several nitrogen ring compounds like purines and pyrimidines. And the first evidence for possibility of prebiotic synthesis of adenine was presented a long time ago by Oro using thermal reading also of ammonium cyanide solution and HCN. So other work using thermal reading and forming adenine was done by Lowen and co-workers. And adenine was observed after heating of a solution of hydrogen cyanide in liquid ammonia. So, but if the ionizing agent is other, for example, energetic electron beam, we produce, for example, we can produce several amino acids and adenine as a product of the irradiation. In this case, the reagents were methane, ammonia, and water. But if we use proton irradiation, the results change. If we use proton irradiation, we cannot find adenine. So here I show you some works where CO and N2 and water was irradiated by proton and adenine was not observed, here also CO, Na3 and water, others important biomolecules was formed. Here uracil, RNA base, here cytosine, here thymine, but adenine was not observed in this problem if we use proton irradiation. So in our work was the first experiment employing photons, in which adenine was formed in a primitive atmosphere simulation and extraterrestrial atmosphere simulation. So the interaction between soft rays and the sample and the ice produce energetic secondary electrons. So maybe we suggest that maybe these secondary electrons are important for adenine synthesis, because adenine was observed only there are electrons involved in the experiment. Discharges or beam electron experiments. So in this work, we didn't find amino acid or other nucleobases like guanine, cytosine, and uracil or thymine. We could not see in infrared. Chromatography didn't find, and nuclear magnetic resonance not also. So we suggest that these molecules have low resistance to the soft X-ray. Almost the same time, we wrote other paper where we investigated the photodegradation of solid phase and gas phase biomolecules by soft X-ray. And we investigate a lot of molecules, and we showed that adenine is at least 10 times less radiation sensitive than uracil and 1,000 times more resistant than amino acids. So adenine is very stable comparing with other molecules. So concluding, we present the chemical alteration produced by interaction of soft X-ray and secondary electrons on Titan aerosol analogs. We simulate 1 million years of the solar soft ray exposure on Titan atmosphere. The presence of traces of water and CO in the sample simulates the cometary bombardment on Titan. Several organic molecules were formed in the ice. The heating changed the chemistry of the tolling. On Titan, the processed aerosols will be deposited along the time at the surface or at the bottom of lakes and rivers, living with them new formed organic species. And gas chromatography and nuclear magnetic resonance analysis of the tolling at room temperature showed several nitrogen compounds, adenine, that is a DNA nucleobasis, when we irradiation tight atmosphere analogs with soft X-ray. It's